Hi guys, it's Inventor Andy and welcome to part 2 of the Serial Flash tutorial. So in the last video we created our Atmel start project and we created the header file and the function definitions for our Serial Flash library. Today we're going to be filling out the function code and creating the rest of that library, and in the final video we will use this library to test the Serial Flash on the Atmel SAM D21 Explain Pro board. So first thing to do today is we're going to create a C file which is going to match our extflash.h file. So if we click add, new item, select C file, and let's call this extflash.c. Okay, first let's include our header file that we created in the last video. And after that we're going to create an array of different flash devices that our board supports. Now at the moment we're only going to include one device, but the idea behind this is if you've got a board that uses multiple different types of serial flash, or if you want to create a kind of a generic library that you can use on different board designs, then all you have to do is input the various manufacturer details into this struct. So our first one is going to be the serial flash device that's already on the board. So the manufacturer is Adesto. The device ID is 0x01. Now we've got this from the datasheet. And the device size is 8 megabits or 1 megabyte. So that's 0x. Okay, now let's just create a blank one here. And there we go. So this structure, we can just add multiple different serial flash devices to this array if we want to cover them in the library. Okay, let's create some variables that we're going to use in the library. We're going to create a pointer to that flash info. Set that to be null for now. Our info buffer, where we're going to store the information. And our receive buffer. So this is going to be the command size plus the page size in memory. So page size plus. There we go. So those are all the global variables we need for this. Now we can start fleshing out some of that function code. So Our first one is we're going to create a blank function for the SPI transfer complete. Probably don't need this, but it's nice to have it there in case we do want to implement something later on in our code. Okay, so if you're wondering where I got the structure of this function from, if we go to our examples and go to driver examples, you can see we've got an example function here for the callback on the serial flash. And that's basically what we've done. We just copied that over with a different name. Okay, next up we are going to create our initialization function. So this is where we set up the SPI device on the microcontroller. So let's get the I/O descriptor. Again, if you're wondering where we've got this from, this has all come from our driver examples. So we're going to call this serial flash, and we're going to copy it into the ext flash IO object that we created earlier. Now we're going to register the callback function. So this is registering our transfer complete function, and this ensures that that gets called once we've done an SPI transfer. So we want to initialize that on the serial flash IO descriptor. And we want to call that on transfer complete. And we want to call this function, so SPI ext flash complete callback. Make sure you delete those brackets at the end. They're not needed as a function parameter. Finally, let's enable the asynchronous SPI on our microcontroller. Okay, so next up we're going to create our method for transferring information via SPI. So this is a function that will get called by other functions for sending a command or receiving data from the serial flash. write buffer, a read buffer, and the total length of bytes that we're transmitting. If you remember with SPI, rather than a send and receive like you do with something like UART, you basically exchange bytes. So the number of bytes you send is the number of bytes that you receive. And we're going to return a boolean for this, so it will return true if it's successful, false if not. Okay, so first we set our initial return value. Now let's create a structure for our SPI status. Now the first thing we're going to do with this is we're going to pull down the chip select pin. So with SPI you can daisy chain multiple devices onto the same data lines, and the way you select between those data lines is by pulling a chip select low on the device you want to communicate with. So we use the GPIO functions to set the pin level of serial flash CS, which is the chip select pin, and we're going to pull it down to 0. Now we're going to transfer the data. We're going to transfer to the serial flash IO. And we're going to start at byte 0 of the write buffer, byte 0 of the read buffer, and we're going to transfer the length number of bytes. Now we're going to wait while the transfer completes. So we do this by creating a little while loop and polling the status of the SPI device. So the SPI device is serial flash, and we're going to store that in the pstep variable we created earlier. So while that's busy, we're just going to add a little bit of a delay. So what we're doing here is we're initializing the transfer with our write buffer, which is the data we're sending, our read buffer, which is the data we're receiving, and the number of bytes that we're transferring. And then what we do is we just continuously poll that SPI device until it says, okay, that transfer is complete. Finally, if we've got this far, our return value is true. Disable SPI chip select again. And we do that by putting it high. And finally we return the function. So this function is going to be used for pretty much any communication with the serial flash device. So that's why we've got that right up there at the top. Our next function is going to be to read the info of the serial flash device. And this again will return bool if we're successful. So the first thing we're going to do is we're going to create our command message. So this is requesting that the device sends back the information. So our first command is flash command MD ID, which means manufacturer and device ID. And then we've got 3 dummy bytes. Set our return value. Now we're going to call our transfer function that we defined above to send that command message. So we're going to send our write buffer. We're going to read the result into the RX buffer, and we're looking for a total of 4 bytes. Now we're going to copy this information into the info buffer. So the first part of the info buffer is going to be the 2nd byte of the RX buffer. And the 2nd byte of the info buffer is going to be the 4th byte of the RX buffer. And finally, if that transfer was successful, we're going to return true. Our next function is going to be verifying that the flash component is valid. So this is where we check against our authorized parts in the above section. So the first thing we're going to do is we're going to read the info in. And if we can't, we're going to return false. Next up, we're going to set that pointer to point to our flash info array. And we're going to loop through the array of devices and see if any of them match the information we've got from the serial chip. So if we find a match, we're going to break out of the loop. Otherwise, we're going to move on to the next device in the array. And finally, we're going to return whether we found a matching device. Our next method is going to be reading the status of the flash device. And again, we're going to return Boolean here. Okay, so first we're going to build the command structure for reading the status. This is a 3-byte command. We're going to use the flash command read status, followed by 2 dummy bytes. Set our return value. Now let's send our command and fetch our response. Now let's copy this into our receive buffer. Which we've specified up here. And we're going to get the first byte from the status register. Now, because we did a successful transfer, we can set the return value to true. And finally, let's return the function. Our next function is for waiting until the serial flash device is ready for another operation. And we're going to return an integer. And we're going to return 0 on success and less than 0 for any kind of failure. So let's create a return value. And we're going to begin a loop where we read the status continuously on the device. And we read that status into our buffer variable we've just created. And finally we check whether the flash status is busy or not. And if it's not busy, we're ready for the next operation. Now, assuming we got this far, we can return 0, which means that the device is now ready. Okay, so our next function is to enable writing on the flash device. And again, we're going to return 0 on success and less than 0 on failure. So let's create a command for enabling write operations. And this is a single byte command. And we're going to set that to flash command write enable. Now we'll set our initial return value to -3. Now let's send the command over SPI. We're going to send 1 byte, and if that transfer was complete, we can set our return value. Which means that we were successful. And finally, let's return our function. Okay, so now we're going to configure our flash device for use. So these are the functions that we actually defined in the header file in the last video, and these are the ones that we're going to use with the rest of the application. So, Boolean, and we're going to use extflash_open. Okay, so first off, let's create our return value, and we're going to default that to false. Now let's create a buffer for the status register. And we're going to call the function that we created earlier to verify our part. So if ext flash verify part, we're going to copy the status register to our return value. And this will return once the device is ready to program. And finally, let's return the function. Okay, so next up we're going to send a read request to read data from the flash memory device. So our first parameter is the offset in bytes to begin reading from. The next is the number of bytes to read. And finally, we want to specify a buffer to store the read data into. And it must be at least that length in bytes. And we're going to return bool. Okay, so let's begin our function. We're going to have a 4-byte write buffer for the command. Let's set our return value to be false initially. And let's wait for our device to be ready. So if the device isn't ready, we're just going to return false. Okay, so we're going to build our read command with our 24-bit read address. So we're using low frequency here, so we don't need to use the fast read command. Which I believe is about 1 megahertz in this instance. So our first byte is going to be the read command. Now we need to start offsetting our 24-bit address. So we're going to bit shift that by 16 bits. And the next byte by 8 bits. Okay, so what we've done here is we've created a 4-byte command which says read from the device and read from this address. So now we're going to get the response. So we're going to transfer the write buffer, our RX buffer, and the size is going to be the length in bytes of the data that we're reading, plus 4 extra bytes, which is for our command and address. Finally, we're going to copy that into our buffer that we initialized as a function parameter. So we're going to use the memcopy function, and we're going to start at byte 0 of the buffer that we want to read into, byte 4 of the buffer of data that was returned from the SPI device. If you remember, we've got 4 bytes worth of read command, so we want to skip over that and start the actual data. And we want to copy the length of bytes. Now, if all this completes, we're going to return true. And and finally we can return the function. Okay, so this is our function for reading data off of the SPI device and saving it to a buffer that we specify. Our next method is to send a write request. So this is how we save data to the flash device. So our first parameter is the offset in bytes, which is the 24-bit address where we start writing to. Next up is the length of bytes that we're writing. Finally, our buffer of data that we're going to write. And we're going to return a boolean again for this. So firstly, let's create our write buffer for the command. Let's create a status variable to store our SPI status. And we're going to begin our write loop. So what we do is we divide the write operation into chunks. So if the data is bigger than one page of data in the device, then we break it up into individual pages and we send the write command for each one of those pages until we've run out of data to write. So well, length is greater than 0. Let's wait for the flash device to be ready. And if it's not ready, we're going to return false. Next up, we're going to enable writing on the flash device. And again, if it's not ready, we'll return false. Oops, let's spell a mistake up there. Now we're going to create a size variable for the length of each instruction. now we're going to work out the length of this instruction. Remember, we're looping through and programming one page at a time. So flash page program size, and we're going to minus the current offset. Left over from the flash program size. Okay. Now we're going to quickly check the bounds of this value. Make sure that we haven't gone less than the length. And if we have, we're just going to set the iLength variable to length. Okay, now let's create our 24-bit address. So our first byte is the program byte, and then we're going to break up the address like we did with our read command. Now we're going to set our new offset and our new length for the next iteration of the loop. So the offset, we add the number of bytes we've just written to it, so we move to the next block in the address. And the length of data that we need to write still, we subtract the number of bytes we've just written. Okay, so we're going to start the combined rect sequence. So there's a series of commands that we do here. So let's make sure our chip select is at 0. First, we're going to write the page program command. Scroll this up so you can see it. So we're going to transfer that 4-byte command, and now we're going to wait until that transfer completes. Do a quick delay and recheck. So our first command is to send the write command and the address that we want to start writing to. And if this doesn't work, let's pull our chip select pin high. And return false. Okay, now we're going to send the actual data that we want to write. So again, we're going to do an async transfer and serial flash, and we're going to write from our buffer, and we're going to read into our RX buffer, and we're going to do this from the number of bytes that we specified with the ilen variable. So assuming we started that transfer, we're going to wait until it completes. So we can just copy this code here, and again with our else condition we can copy that as well. Finally, let's pull our chip select pin high, and we're going to move through to the next iteration of the loop. So increment the buffer. So what we're doing here is we're moving the pointer of where to write the data from by the number of bytes that we've just written. And finally, if all of that completes, we can return true. Okay, so the next command we're going to write is the erase command. So we've got another offset parameter here, which is the address that we're going to start erasing from. And then we're going to specify the number of bytes that we're going to erase. Finally, we're going to return a Boolean. So let's create our write buffer for the command. And that's 4 bytes, so 1 byte command plus 3 byte address. And we're going to create 2 size variables, so 1 to keep track in our loop, and 1 for the total number of sectors we're going to erase. So first, let's set our erase command. Now we're going to set our offsets. So the end offset is the last address that we're going to erase from. So we start with the start address, and then the number of bytes that we're erasing minus that last byte. Our offset we're going to divide by the sector size, now finally we're going to work out our number of sectors that we're going to erase. So that is our end offset minus our offset plus the flash erase sector size -1 divided by the flash erase sector size. So now we know the number of sectors that we have to erase based on our start and end addresses. So the next thing to do is to loop through and perform the erase commands. So let's wait until any previous operation is complete. And if it's not, we're going to return false. Next up, we're going to enable writing on the device. And again, if that's not complete, we're going to return false. Okay, let's scroll up a little bit here so we can see it. Now let's create our address for erasing from. And finally, we're going to send the erase command. Now, we're not actually doing anything within this loop, so we'll just leave that empty for now. Finally, once we've looped through all of the sectors and erased, we can return true. Okay, so there we have it. It's quite an intense file, but once you've written this, you can pretty much use it for any SPI serial flash device. You've just got to change or add to this array here with your different manufacturer and device IDs. So let's save this and let's give it a quick compile. Make sure we haven't got any errors there. Okay, 0 errors and 1 warning for return value. We can look at that later. So in the next video, I'll show you how to use this library in an actual application to read and write to the SPI flash. Thanks for watching, guys. See you soon. Hi guys, it's Inventor Andy here. Thank you for watching my video. If you like the video, please click like, please subscribe to my channel, and please feel free to add any comments if you've got any suggestions for tutorials or videos that I can do. Thanks very much, guys.